Find all asymptotes, intercepts, and or holes and use them to graph the following rational function. We'll start by factoring the numerator and denominator. The denominator is relatively easy. Since a is 1, we can just ask what two numbers multiply to negative 12 and add to 1. That would be 4 and negative 3. The numerator has a leading coefficient of 2, so we need to use the AC method to factor. A times C is 6. Two numbers that multiply to 6 and add to negative 7 are negative 6 and negative 1. So we'll rewrite the quadratic using negative 6 and negative 1. Now factor by grouping. Continue factoring, pulling out x minus 3, and we're left with 2x minus 1. So we'll replace the numerator with the factored form, x minus 3 times 2x minus 1. To find domain, we'll set the denominator equal to 0. And since we have it in factored form, this will be relatively easy. Set each factor equal to 0. And we get x equals negative 4 and x equals 3. But these are actually restrictions, so we'll say not equal to. So the domain is all real numbers except for negative 4 and 3. In interval notation, that will be negative infinity to negative 4, union negative 4 to 3, union 3 to infinity. To find vertical asymptotes, we want to find zeros of the denominator after it has been reduced. Notice that x minus 3 and x minus 3 occurs in the top and the bottom. So we can reduce this to get 2x minus 1 over x plus 4. And now we're going to focus on the denominator of the reduced rational expression and set it equal to 0. So x plus 4, set it equal to 0. Solve, we get x equals negative 4. This is the vertical asymptote. Holes in the graph occur with the factor that gets canceled. So we can see that if we set x minus 3, the part that canceled, if we set it equal to 0, we get that x equals 3. That means there's a hole at the x value of 3. To find the y coordinate, we will plug 3 into the reduced fraction here. So 2, replace the x with 3, minus 1, over, replace the x with 3, plus 4. We get 5 over 7. That means the hole is at 3, 5 sevenths. To find a horizontal asymptote, we compare degrees. Look at the degree of the numerator and the degree of the denominator. The degrees are the same. If the degrees are the same, then we'll look at a ratio of the leading coefficients. So the numerator has a coefficient of 2 on the lead term. The denominator has a coefficient of 1 on the lead term. So 2 over 1, or simply 2. Y equals 2 is our horizontal asymptote. Since we have a horizontal, we will not have an oblique asymptote. To find x-intercepts, we set y equal to 0. And since we have a rational function, we can take a shortcut and simply set the numerator of the reduced fraction equal to 0. So 2x minus 1, set it equal to 0, and we get that x is equal to 1/2. 1/2, 0 is our x-intercept. To find the y-intercept, we set the x's equal to 0. And it's easier if you use the original function. Notice that this term will go to 0, this term will go to 0, this term will go to 0, this term will go to 0. So you're left with 3 over negative 12, which reduces to negative 1/4. So our y-intercept is 0, negative 1/4. If we take all of our information, we can put it together on a graph. We have a vertical asymptote at x equals negative 4. We have a horizontal asymptote at y equals 2. Some points that we know are on the graph are the x-intercept, which is at 1/2. The y-intercept is at negative 1/4. We also know that there is a hole in the graph at 3/5/7. So 3/5/7, we have a hole in the graph. And that's really all the information we have. On the right side, we can assume what's happening here. We have this curve approaching the asymptote, then the hole connects to these two intercepts, and then it drops down as we approach the asymptote. We don't have any information on what's occurring on the left side, but we know there's got to be something there because of the domain. The domain said that there's everything except for negative 4 and 3. So to get the points that we have over here, if we wanted to do it algebraically, we could just plug in some values into the original function. For example, plug in negative 5 into the original function and see what it spits out, what the y value is. Plug in negative 6, see what it gives you, plug in negative 7, and so on to get a bunch of points to plot up here. But for our case, we're just going to graph it in the calculator, go to y equals, type in your function, and then hit graph. And we can see that the curve is up here between these two asymptotes. Again, point plotting will get us some values algebraically. We're just going to use the trace key to get a point to start with. I need to scroll over to the left, and I'm just going to get that point around here. It looks like it's around negative 6, 6. Not exactly, but we're just approximating. So negative 6, 6 is roughly here. From there, we'll just sketch a curve that approaches the vertical and horizontal asymptote and goes through that point. Not very accurate, but all we want is a very rough sketch. The main thing that we're focusing on is going to be the algebraic steps prior to graphing. You want to make sure you can find the horizontal and vertical asymptotes, the domain, holes, and intercepts. Find all asymptotes, intercepts, and/or holes and use them to graph the rational function. We'll start by factoring. Notice the numerator has already been factored for us. We only need to factor the denominator. We need two numbers that multiply to negative 6 and add to negative 1. That is negative 3 and 2. To find the domain, we set the denominator equal to 0. And we'll use the factored form. That'll make it a little bit easier. Set each factor equal to 0 and solve. We get x is 3 and x is negative 2. And we'll actually say not equal to because those are the domain restrictions. Writing this out in interval notation, we would get negative infinity to negative 2, union negative 2 to 3, and then union 3 to infinity. To find vertical asymptotes, we reduce and look at zeros of the denominator. Notice in this case, there's nothing to reduce. We don't have any common factors in the top and the bottom. So we'll just set the denominator equal to 0. We've already done the work here. We set the denominator equal to 0 and found each of those x values. So we get x equals 3 and x equals negative 2 as our vertical asymptotes. We don't have any holes. Remember, holes are generated by factors that are common to the top and the bottom. Those factors that reduce, those will generate holes in the graph. To find a horizontal asymptote, we need to compare degrees. Notice the degree of the numerator is 1 and the degree of the denominator is 2. Whenever the degree of the top is smaller than the denominator, then the horizontal asymptote is simply y equals 0, basically the x-axis. If you have a horizontal asymptote, we're not going to have oblique asymptotes. To find the x-intercept, we'll set the numerator equal to 0. 6 times x minus 1. Set it equal to 0. X minus 1 equals 0. And x equals 1. So our x-intercept is 1, 0. To find the y-intercept, we make all of the x values 0. So we have 6 times 0 minus 1 divided by 0 squared minus 0 minus 6. This gives us negative 6 over negative 6, which is 1. The y-intercept is 0, 1. We have our vertical asymptote at 3, x equals 3. And at x equals negative 2. The horizontal asymptote was the x-axis, y equals 0. And then some points that we know are on the graph are the x-intercept of 1 and the y-intercept of 1. It looks like in the middle we've got this curve. But we don't have any more information about the left and the right. We know there has to be parts of the graph on the left and the right because we know the domain says so. So algebraically, if we wanted to find some more coordinates to plot, we would use point plotting. Pick 4, plug in 4 to the function, and see what the answer is. Plug in 5, see what you get, and so on. We could get a bunch of points that way. But for us, we're just going to use a calculator to get a rough sketch. So we'll go to y equals, plug in the original function, and then graph. And we can see that the middle portion does look correct. Looks like we got that right. And then to get this piece on the right and the left, we'll just trace and get some values. So I need to scroll a little bit. I'm just going to get that point here. Looks like that's roughly 4, not quite 3. So 4, 3, roughly right here. And we have that curve. Again, it's approaching those asymptotes. And again, we'll trace and go to the left and see what the point is over here. That point, roughly negative 3, negative 3.5. Again, just approximating. And we now have our curve on the left. So this is just a sketch. It's not very accurate, but that's okay. We're just going for a quick sketch. The main thing that we're going to be concerned about in this course is algebraically finding the asymptotes, the domain, holes if they exist, and x and y intercepts. Find all asymptotes, intercepts, and or holes and use them to graph the following rational function. We first want to factor. So looking at the top, we'll have x, and then two numbers that multiply to 5 and add to 6 are 5 and 1. Then the denominator will just copy. So domain, we set the denominator equal to 0 and solve. x equals negative 2 is actually a restricted value. So using interval notation, domain is negative infinity up to negative 2 union negative 2 to infinity. To find vertical asymptotes, we first want to reduce the rational function if possible, and then look at zeros of the denominator. Notice that you do not have any common factors in the numerator and denominator, so there's nothing to reduce. That means we simply set the denominator equal to 0, similar to what we did with domain, and solve. We get x equals negative 2. This is the equation of the vertical asymptote. To find holes in the graph, we look at any factors that reduce. Looking back at the factored form, notice that nothing reduces, so we don't have any holes in the graph. To find horizontal asymptotes, we compare degrees of the numerator and denominator. Recognize that the numerator has a degree of 2 and the denominator has a degree of 1. If the degree of the numerator is bigger than the denominator, then there are no horizontal asymptotes. If the degree of the numerator is 1 more than the degree of the denominator, then we can look for an oblique asymptote. Now typically we have to use long division to find it, but since the divisor is linear, we can actually use synthetic division to make the process a little bit faster. So we'll start by copying the coefficients of the numerator. Then inside the box, we'll put the opposite of the number that you see in the denominator, that meaning negative 2. So we'll drop down the first number, multiply, negative 2 times 1 is negative 2, add and we get 4. Repeat that process, negative 2 times 4 is negative 8, add and we get negative 3. Negative 3 is a remainder. We're just going to ignore that. It's not part of the oblique asymptote. All we care about are these first two numbers. We'll translate those back into an equation, that being y equals x plus 4. To find x-intercepts, we set the reduced numerator equal to 0. In this case, nothing reduced, so we simply set the factored form of the numerator equal to 0. Set each of those factors equal to 0 and solve. X equals negative 5 and x equals negative 1. If we write those as coordinates, that would be negative 5, 0 and negative 1, 0. To find y-intercepts, we want to make all of the x's 0. And it's easiest if we go back to the original equation and find out what f is when x is 0. We have 0 squared plus 6 times 0 plus 5 divided by 0 plus 2. That is 5 halves. Or as a coordinate, 0, 5 halves. Now we can take all of this information and put it together on a graph. I like to start with the asymptotes. The vertical asymptote is x equals negative 2. We'll represent that by a dotted line. We have the oblique asymptote, y equals x plus 4. The y-intercept is 4, and then the slope is 1. Again, we'll represent that asymptote with a dotted line. And then some coordinates that we know are on the graph are the x-intercepts of negative 5 and negative 1. We also know that the y-intercept is 0, 5 halves. And this is really all the information we have so far. The right side, we can get a sketch. We have this curve that's approaching the asymptotes, and it goes through the two intercepts. And on the left side of the vertical asymptote, we really only have this one point. if we wanted to get some more points algebraically, we would simply plug in some values. Say -3, plug it into the function, see what the y value is, plug in -4, and so on, and get some points that way. For our example, we're going to use the calculator. So we'll go to y equals, and alpha y equals will give us the pretty fraction that we can make the typing process a little bit easier, and type in the original function, x squared plus 6x plus 5, and that is divided by x plus 2. Then we'll hit graph, and we can see our function looks pretty good. To get an additional point over here, I'm just going to use the trace key and get an approximate value. So this looks good enough. Roughly -3, not quite 4. So -3 and almost up to 4. We have an additional point that we can use to play connect the dots to draw our curve. And we now have a sketch of the rational function. Find all asymptotes, intercepts, and or holes and use them to graph the following rational function. We'll start out by factoring the denominator. The top doesn't need to be factored. Notice the denominator is a difference of squares. We can factor that as x minus 2 and x plus 2. This will help us find the domain. To find the domain, we set the denominator equal to 0. We can use the original form or the factored form. Does not matter. Factored form is typically the way to go. Set it equal to 0, and then set each of those factors equal to 0, and solve those independently. We get x equals 2 and x equals -2. And these are actually restricted values, so we're going to say not equal to. Using interval notation, the domain would then be -infinity to -2, union -2 to +2, union 2 to infinity. To find vertical asymptotes, we set the reduced denominator equal to 0. Notice that none of the factors are the same in the top and the bottom, so nothing reduces. So set the denominator equal to 0. Very similar to what we did for domain. We'll see that we get x equals 2 and x equals -2 as our two vertical asymptotes. Holes in the graph occur when you have factors that reduce or cancel in the numerator and denominator. Nothing canceled or reduced here, so no holes. To find horizontal asymptotes, we compare the degrees of the top and the bottom. The degree of the top is 1, the degree of the bottom is 2. If the top, the numerator, has a smaller degree than the denominator, then the horizontal asymptote is automatically the x-axis, or y equals 0. Since we have a horizontal, we do not have an oblique. To find x-intercepts, we'll set the numerator equal to 0, -3x equals 0, and solve. We get x equals 0. As a coordinate, that would simply be the origin, 0, 0. To find y-intercepts, we make all of the x's 0. So we have -3 times 0 over 0 squared minus 4. That's just going to give us 0 over -4, or 0. That is the origin as well. To sketch this, we'll start by graphing the asymptotes. We had a vertical asymptote at x equals -2. We'll represent that with a dotted line. Also at x equals +2. We have a horizontal asymptote at y equals 0, or the x-axis. And we know the point 0, 0, or the origin, is on the graph. And so far, that's the only point that we know according to our previous algebraic steps. If we wanted some additional points, we would use point plotting. For example, we would plug in -6 to the function and see what we get, plug in -5, -4, and so on to get some additional points. For what we're going to do, we'll simply use a calculator to get some additional points. So y equals, then type in the original function, alpha y equals will give us the fraction look, and we have -3x, and that is divided by x squared minus 4. And we'll go to the graph, and from here I'm going to use the trace feature to get some additional points. We'll start on the left and just get an additional point. That's roughly -3, 1.75. We use that to get a point to plot. An alternate way to do this is to go to the table. We can hit second table and get some points. Look for any points that might be easy to plot, like -1, -1 we know is there, and 1, 1 as well. That will give us that middle section. And then if we wanted to go to the right, say around 3, we have 3, -9/5, and we can get an approximation of that as well. Sketch that part. And we have a very rough sketch of this rational function.